Okay, now, had an immediate question about this. What does 40% solution mean? Okay, so clarification. And the question is actually phrased very nicely. Is it 40% antifreeze or is it 40% water? Okay, so the convention is this means the 40% of your solute, your antifreeze in this case. 40% solution means 40% antifreeze. And then immediately a couple of fractions. Okay, and it wasn't necessary to do the fractions, but it can be done. Usually we'll end up just using the percents rather than converting them to fractions. Simply because the fractions get kind of unmanageable. But if we stick with percents, we can do it. But here's a repeat. We have 20% solution is 1/5. One-fifth antifreeze. So 1/5 of 10 liters, I'll abbreviate liters with a capital L. For 2 liters is antifreeze. And then well, obviously, not so obviously, but 40% is 2/5. And not everybody, unfortunately, would know that immediately, but everybody in the class was extremely well prepared for this class. People know this. So 5 liters, 2/5 antifreeze. Two-fifths of 10 liters equals, coincidentally, 2 liters. Okay, well, the next question comes, okay, now we know we have four liters of antifreeze, and there's a total of 15 liters of solution. And also, $11 liters of water. So one thing some people did was they divided the 4 liters by the 11 liters of water, which is not an unreasonable thing to do if we haven't defined what a percent solution means. Okay, but if we think back, we took 1/5 of the whole 10 liters to get to 2 liters. So we're going to base it on the total amount of solution. Okay, we take whatever percent of total amount of solution and what I pointed down here. 2/5 of 5 liters is 2 liters, it's 5 liters of this solution. Okay, so we're gonna I'm just thinking I want to write this down. I'm gonna say the fraction of the solution, which is antifreeze, is 4 liters over 15 liters. Yeah, let's just better. We'll do. Okay. And 4 divided by 15 is 46. Well. Or 2.6 repeated, but if we ran that, seemed obvious to me. 4 into 15 is 3. Wait a minute. 2, 6. Yes, I did. 15 into 4. 4 into 15. Couldn't go to that. 15 into 4. You know, 2 15 is 30 with 10 left over. 10 15 is 2/3. So it would be 2 2/3. Comes up 0.26 and 2/3. Whatever way you think about it. If you have to punch it into the calculator, that's okay. But there we have it. That's the fraction, but that fraction means 26 2/3%. Okay. And if you do fractions, it's 26 2/3%. Now, usually we'll stick with percents rather than fractions, but we want to think fractions and how fractions relate to the percents. Okay, well, let me take this a little more. Here's one question we can ask. The standard question is, okay, got this, and we want to get a 32% solution. How much of this do we have to add to this to get a 32% solution? Okay, that's a typical question. We're going to do a transition. We're going to do a slightly simpler question first. Actual, okay, as I was thinking about it, I just realized that what I was going to do wasn't going to be a transition. It's going to be the whole problem. Okay, so let's look at it this way. You have 6 liters of 40% solution with 10 liters of 20% solution. What's our new percent? 100 that. And we'll move on. All right. So. Did pretty well here. So it was our strategy here. We found how many liters of antifreeze we have in the 10%, the 20% solution, and how many liters we have in the 40% solution. So we're going to do the same thing. Except we no longer have 5 liters of 40% solution. We have X liters. Okay. So we're going to write this out a little more carefully. And we have 2 liters of antifreeze in the 20% solution as before. How much? The 40% solution. Well, we have X liters for 40% solution. We got 0.40 liters of antifreeze. So now we know we have an expression for how much antifreeze. So here's our total antifreeze. 2 liters plus 0.40x. And if X happens to be 5 liters, well, 0.40 times 5 liters is 2 liters. We get the 4 liters that we have in the original problem. We've got all the numbers. Then what's the total amount of solution? Well, the total amount of solution is X liters of 40% and 10 liters of 20%. That's X plus 10 liters. The fraction of antifreeze is 2 liters plus 0.40x divided by X plus 10 liters. Okay, well now, if our solution is supposed, if we want to get a 32% solution, can we write an equation? This way. What a 32% solution? What equation would we want to solve for X? And so if we want a 32% solution, what equations we solve for X? Well, this is really obvious to everybody. This is our fraction of antifreeze, right? And this fraction should give us 32%. Okay, so the fraction of antifreeze is 32%. And what's 32% mean? Make sure we understand that. Thirty-two percent is a fraction. It means 32 per 100%. Means per 100. I'm sure you know that. So that means 32 over 100, but that's easy to write as a decimal, 0.32. So we're going to use the decimal form for all this. So if the fraction of antifreeze is this, and the fraction of antifreeze is this, then this plus this is 0.32, and all we have to do is solve the equation. And the equation is easy to solve. We're going to multiply both sides by the denominator. So rewrite it. We multiply both sides by X plus 10 liters. Of course, we've got to be careful. We don't want to multiply by 0, but we don't really have to worry about that because for this to be 0, X would have to be negative 10 liters. And you can't add negative 10 liters. Actually, you could. You'd take 10 liters away, then you'd have no solution at all. So it wouldn't be a solution, okay? But this is not really an issue because we're going to, X is obviously going to be positive. Okay, so, and you also can't take a couple of liters of 40% solution out of 20% solution. 20% solution all mixed up. You can't do that. Okay, well, aside from that, here we have this. We multiply both sides by the denominator. Now, one thing that we'll often do, but we don't really have to in this case, I don't think that that's going to be a good idea. We don't like dealing with decimals. We could multiply both sides by 100. To make that 4x and make that actually make that 40x, and this would be 32x. Then we'd have to multiply this by 100. We'd have 200 liters over there. We'd have 320 liters. Okay, and that's always an option, and a lot of times it's a really good idea. But in this case, it isn't such a great idea because the numbers are simple enough. So that's a matter of taste. We could always do that. Using this derivative law. And now we bring our X's over here and our liters over here. We're going to have We're gonna subtract 2 liters from this side. We're gonna subtract 0.32x from this side. So on this side, the 2 liters will subtract off, and we just end up with our 0.08x. Looked at it and realized I wasn't gonna have, I wrote it off that way. So we do that 0.32x. 3x. They subtract the same thing from both sides, and we end up with 0.08x equals 1.2 liters. From line looking at this stuff, okay. And then we can divide 1.2 by 0.08, we're gonna get 15, it'll be 15 liters. Now, just to demonstrate here, I multiply both sides by 100. Just so I'm dealing with whole numbers rather than decimals, because it can get confusing. Is that 1.5 or is that 15? We divide this by this. You got all the decimals to work with. And when you're dealing with percents and equations and the decimal expressions, it often is a good idea to multiply by them. So I'm going to do that. And I get 8x equals 120 liters. X is 120 liters over 8, which is 15 liters. There it is. We check solution. Has 6 liters. I don't have room to write on antifreeze. Just drop down anti there. But we can check this has 6 liters of antifreeze. Ten liters of 20% solution has 2 liters of antifreeze. So we have 8 liters of antifreeze in 25 liters of solution. 10 liters we started with and 15 liters we just found. And eight liters divided by 20 liters, 0.32, that checks out. So we always do want to check at the end. It's pretty easy to check in a mixture problem. Another comment, I'm keeping the liters on the numbers that have liters on them. Now, when we say we mix X liters, we don't write a liter on X, because X is the number of liters. We know that X is going to be the number of liters, or at least we hope it's going to be. And you notice that in doing all these calculations, carrying the liter through all these calculations, we did end up with X equals 15 liters. Okay, if we wrote X liters here, then X would be 15. X is supposed to be the number of liters, X doesn't, the number doesn't include the liters. That might be a little confusing, but that's one option for carrying the units through the problem. And that's, I think, a good idea. If you get used to it, it doesn't confuse you. Because if this didn't come out in liters, we'd be pretty sure that we did something wrong. So that's kind of a built-in check. I think if Open Math is probably not going to tell you to do that in its videos. And a lot of times text won't tell you to do that. So that's your option. I'm not going to get after you if you don't. But if you make the mistakes that you would have caught by doing that, I won't penalize you, except for just a mistake. Won't penalize you for not doing that. But I'll say that. Remember, if you've done this, it would work out. It's a balancing act. Is it worth the potential confusion to keep that in there? Or not? So you figure it out. I think you'll have no problem with it. Okay, let's, let's. This is the one that drove me nuts. Back when I was taking algebra 1 at the age of 3, I was 14. I started my freshman year at 13. Unusual in high school. The younger students in my class, but by the time we got to the next response, I'm pretty sure I wasn't 13 for that long after the school started. Okay. So the shoes cost $7 a pound. Maintenance costs $3 per pound. Two ways to phrase this, but we're going to phrase it the easier way. Okay. How many pounds of peanuts do we add to 25 pounds of cashews? You get a mix worth $4 a pound. Okay, good. So, had a little glitch in the solution, but approach quite good. Should be pretty obvious. You're going to let X equal pounds of peanuts. You want to write that out, keep reminding yourself of what X means. Now, we want $4 per pound, so that we could start We want the total cost over the total weight. Equal. Or, and I'm not gonna keep the units on everything here. This unit's a little more involved and I want to avoid the confusion, but then maybe I'll decide to talk about how it would look if we use the units throughout. Okay, so we're just gonna do total cost over total weight equals 4. Now, what's the total cost? It's I really want to use units. It's $7 per pound. Times 25 pounds. This means. Which means $7 per pound times 25 pounds. And we know that that's going to give us $125. Dollars divided by pounds times pounds gives you dollars. Okay. So I'm going to write it out like this. Not totally comfortable doing that, but I'm going to do it anyway. And then plus, you got X pounds of peanuts at $3 a pound. That's going to be 3X. Okay. So there's your total cost. And the total weight. Is 25 pounds plus X. So total cost over total weight equals 4. Total cost is seven times 45 plus 3. Then we have 45 plus X here. That equals 4. We solve for X. So that gives us 7 times 25 plus 3X equals 4 times 25 plus X. Multiply both sides by the common denominator, but the only denominator in this case. And again, we want to be careful. We want to make sure our denominator can't be 0. But X is not going to be negative 25 pounds. Not taking pounds away. We got to use some peanuts. Okay, to get the cost down for $4 a pound. Okay, so that's going to be 175 plus 3X equals 100 plus 4. I saw the 3X and the X. I'm going to do X squared. My eyes are just not with the right stuff. Okay, if you have this, so this rearranges. Then we're going to get actually for 75. Is that a group or solution? Good. I always have to know it's I can tell whether I've done it right. Okay, now to find out if I've done it right, since I don't always have you around to check me. We'll see if this works. Okay, so $35 pounds of peanuts was $245, right? $3 a pound, 3 times 75 is $245. You won't do that in your head. Keep that if you could. You wanted to. Maybe you do. Okay, then we add these and we get a cost of $400. And we add these and we get 100 pounds. Well, $400 for 100 pounds is $4 per pound. So don't really have to do any further with that because we can see. Still, we can write it down. I've got a little bit. So. The cost of the weight to be dramatically erratic. And it works out. Okay. Another way of stating the problem, and we're probably not going to have time to work it out. But if you choose to think about it, it's up to you. You've already exceeded expectations in this course. Same information, but we want 60 pounds in the mix. Okay. So how many pounds of cashews? And how many pounds of peanuts? Go ahead and see if you get a good start on this problem. Now, you could, of course, find the correct solution. You want 60 pounds, you know what it takes to do 100 pounds. So just take 60% of the numbers we got a minute ago. But pretend you don't know that, okay? Okay, I mentioned that we could do 60% of whatever we got before. I kind of got you off of the wrong track, and that was a mistake on my part. But let's say we let X equals what? Well, we got two things here we don't know, right? Why don't we let X equal the pounds of, I don't know, well, cashews or peanuts? Tell me. Cashews, peanuts, cashews. Okay, what are we gonna do about the weight of the peanuts? We'd let it be Y, but then we'd have two variables. Okay, well, it's actually simple, and you would probably think of it, except we don't have time to do any more thinking. We've got less than a minute to go. If X is a weight of cashew, then weight of the peanuts is 60 pounds minus minutes, right? So now we have an expression for the weight of the cashews and an expression for the weight of the peanuts. And we want total cost over total weight. Equal four. Dollars per pound. So with that information, if we had just a little longer, I believe you'd be able to work it out. All right, well, we've taken a look at this situation. But let's make sure we understand the situation. We got an EMF, 6 volts here, okay? If we close the switch, this capacitor, which is initially uncharged, it's gonna start charging. And ultimately, we're gonna write a simple differential equation for this. Now, y'all have had a differential equations course, but this is a differential equation you get halfway through the first year of calculus. And it's gonna be like dx dt equals kx. It's gonna give you an exponential solution. Okay. But let's see how that develops. So the information is the current's going to start flowing. Means the charge is going to be transferred from one plate to the other. Actually, electrons are going to go this way, but it's like taking positive charge off of here and pushing it through here. Okay. Positive charge gets attracted to the negative terminal. The chemical reaction or whatever it is that's creating this EMF pushes it over to the positive terminal, and then that pushes it away and pushes it up here. That's how it works in a battery. And analogous in other sources of EMF. The rate at which charge accumulates is equal to the current, because the current is what's being pulled off of here and pushed onto here. Okay, if you got a current of 4 amps, that means you're taking 4 coulombs off of here every second and pushing it onto here, or a negative 4 coulombs here and pushing it back here. Okay, your current's flowing in this direction. So the rate at which a charge accumulates is just the rate at which charge is being pulled from one plate and put on the other. It's the rate at which then charge is accumulating on the capacitor. We understand that. It's not hard to understand, but you got to keep thinking about it. You got to think it through a few times before it comes to action. At least I did. Okay, so there's the given information. Rate at which charge accumulates is equal to the current. Because that's exactly what the current is doing. It's accumulating charge. Okay. And the voltage of the capacitor opposes the voltage of the source. Very good reason for that. You're pushing positive charge from here to here, or negative charge from here to here. Either way, you get a positive charge here and a negative charge here. Positive charge here would push positive charge in this direction, and this positive terminal is pushing positive charge in this direction. So opposing. Okay. Another way of looking at it is you're putting charge at the capacitor, the charge here is repelling the charge here. Okay, let's get pushed back. Anyhow, so bottom line, and I realize I'm talking to engineers, and engineers tend to operate just by the rules without the insight. And because there's so many rules, engineers got to follow. Okay, remember we're focusing on the inside here because where you're going to be tested is going to be on inside as well as typically. Okay, so we don't want to just do this by equation. We want to do it by understanding what's going on. And of course, in engineering, you would certainly understand that much. You'd certainly work to understand that much. At some point in engineering, it gets overwhelming, and you got to follow formulas and rules and software and all kinds of stuff. I'll do that in here. Okay, till you need to. Voltage on the capacitor voltage opposes the voltage of the source. So at some point, the capacitor voltage is going to be 2 volts. Accumulated enough charge on there, the capacitor voltage is 2 volts. What's going to be the current at that point? Yeah, number, yeah, bullet figures. Going to be probably a decimal. Well, what's the voltage across the resistor? Because that gives you the current. Okay. Voltage across the resistor. You've got this thing pushing 6 volts, pushing with a potential of 6 volts. Okay. I almost want to talk about a force, but you know, and it is a force. Is the potential creates an electric field in the wire, which represents a force on electrons. Okay. But 6 volts pushing this way, 2 volts pushing this way. What do you got here? At 4 volts. Now, that's intuitive. Kirchhoff's the first law or second law. I never paid any attention which one's first or second. But one of Kirchhoff's laws is that the voltage around the loop has to add up to 0. Voltage drop along the loop adds up to 0. So let's look at voltage drops. Now the answer to the question is you got a net of 4 volts across here. And we're going to work that out very carefully to make sure we're right. Okay, which gives you 0.4 amps. 0.4 amps is 0.4 coulombs per second, and that is the rate at which charge is being accumulated in the capacitor. That's the current. Current is coulombs per second. That's a rate of charge accumulation on the capacitor. If that's what's going on in the circuit. Okay. Let's draw this circuit a little bigger. A little bigger so I can label something. Draw some stuff like that. A capacitor can be drawn with 2 straight lines, but I usually curve one of them. Now that means something to oriented capacitor, regulated capacitor. But I'll usually draw the curved line just because my drawing is sloppy. You don't want to confuse it. Including it. Okay, so here's a loop. Now, what are the voltage drops around the loop? We got 6 volts here, 2 volts here, and voltage drop. Here comes this. Okay, so from here to here, your voltage drops. Well, as you go across here, what's your voltage drop? Voltage drop, or does voltage go down from here to here, or does it go up? Goes up, so voltage drop is negative. Okay. Okay, well, note that this is positive. Let's note that this is positive. Because if this is negative, this thing can suck it all back. Okay. And it's been accumulating, it's been pushing positive charge out here. Said that 3 or 4 times, but there's repeating. Okay, so this is positive and this is negative, and this is negative. Okay. So we go from here to here, Is the voltage drop or gain? Drop, gain or drop? We go across the capacitor in the direction of this loop. It drops. It goes from positive to negative. That's a drop. Okay. So. And it's IR across the resistor. And I've assumed a current in this direction. If I'd assumed in this direction, it would be negative IR because it drops in the direction of the current. Third drop says then that negative 6 volts plus 2 volts plus IR equals 0. And you don't need to do the arithmetic there. IR is 4 volts. Point 4 amps, which is 0.4 coulombs per second. So you're gaining 0.4 coulombs every second on this capacitor. Now that doesn't last because as soon as you start gaining 0.4 coulombs per second, you get more charge on the capacitor instantly. And now all of a sudden you're gaining less than 0.4 coulombs per second because the capacitor has greater voltage and this goes up. And when this goes up, this goes down. Be very, very clear on that. Because as soon as you're clear on that, everything falls into place. You got a simple differential equation, and you got an exponential accumulation chart. Okay, we're going to work through, but that's what's going to happen. And remember, most basic things in the differential equations course, and also we learned in first year calculus, because I'll base this course on differential equations. This is what he's added. I mentioned it. Remember your first year calculus. Okay. Remember first semester. Okay. Anyhow. We get an answer there. And then the other answers. So go ahead and work them out. I'm just going to write this down. We have it for reference. Okay, now everybody, notice how I wrote down the answer to the first question. I did 6 volts minus 2 volts for the obvious reason that you've got 2 volts in this, which gives you 4 volts across the resistor. Same reasoning tells you're going to have 6 volts minus 4 volts over 10 ohms, which is 0.2 ohms per second. That on the wrong place. Down here. Well, if you've got 6 coulombs on the capacitor, and it's 2 coulombs per volt, how many volts do you have? Well, if it's 2 coulombs per volt, that means you're going to have well, let's it means if you have 2 coulombs, you'd have 1 volt, right? 2 coulombs would go with 1 volt. So if you got 6 coulombs, that would go with 3 volts. That's intuitive. And that's a reciprocal relationship. It's not totally intuitive. So you could write that out as an equation. I'm going to use a capital fancy C to distinguish this B from this C. Well, right. The definition of capacitance, which you should know, is you did spherical insulating the capacitor in the previous chapter. It's a number of coulombs per volt. So what I've given you is Q. And you know the capacitance, so you solve for V. The V is going to be Q over capacitance. Thank you. 6 coulombs over 2 coulombs per volt gives you 3 volts. Okay. So if we place to write this down, again, I can squeeze it in down here. Six coulombs plus 3 volts across the capacitor. Implies with 3 dots, the same reasoning. Point 3 coulombs per second. 0.3 amps. Because you're going to have 3 volts across there, 6 volts here, 3 volts there. All right. So let's just kind of orientation to how capacitor behaves in the circuit. So let's now go to the important question. Capacitor holds charge Q. What's the rate at which Q is accumulating? So it's the same question I asked here, except now it's for an arbitrary charge. Okay, arbitrary Q. So in symbol, how does it work out? Okay, the capacitor holds charge Q. What's the rate at which Q is accumulating? Well, what's your key here? In every case, you needed to know voltage across the capacitor, right? Once you know the voltage across the capacitor, you subtract that from the voltage of the source, and you get the voltage across the resistance. And you got the current. Okay, so the key. So when you're thinking this through in your problem solving, you think back to what you did here. In each of these cases, as soon as you knew what the charge was here, you got it. Okay. Let's just look again. When you knew that the charge here, I'm sorry, when you knew what that the voltage here was 2 volts, then you knew that the voltage across here was 4 volts. And you immediately were able to get the current. Okay. When you had 4 volts across here, well, you were immediately able to get the current. She was, you had to know this in each case. And down here, what? You had to find this, and as soon as you have this, that comes about immediately. And easily, since I chose nice round numbers for the resistance. Okay. That's the key part of it. Okay, well, then definition of capacitance is charge per unit of potential. Okay, charge per volt. V equals Q over C. C being again capacitance. We know V equals Q over C. Potential drop. What's a resistor? Is I'll call this V sub C, the voltage across the capacitor. It's only one resistor. And I'm stepping ahead of myself. Better if I insert. It's been right on R. Right there. Okay, hold and cross resist. See that? The expression current is voltage across resistor divided by R. Okay, well, you can work that out. But since I just gave you Q as a symbol. We really don't need much more than this. The current is source minus source potential minus forward across capacitor divided by resistor, which of course that equals this. Okay. Well, what's I? I is the rate at which current is, at which charge is accumulated. What's the rate of accumulation of charge? It's dq dt. And because the charge is always changing, dq, you got it right. This is a derivative. Okay. The rate of accumulation is always changing. The rate of accumulation is dq dt. So simple linear differential equation. We solve. Okay, again, I'm leaving these as 3 dots. You probably ought to review differential equations. You don't immediately see how to do this. Okay. It's simple linear differential equation. And then you get your QT reasoning. Okay, the intuitive result. The voltage across the capacitor is eventually going to approach exponentially. Turns out. Well, this is going to continue. You're going to continue to do current until the voltage across the capacitor is equal to the voltage of your source, in which case then current's going to cease. And current's going to continually diminish because the charge on the capacitor is going to continually increase. Okay. Actually, I said something was going to diminish. I don't even remember what the words were. Let me make sure I said that clearly. Yeah, I said the current is going to diminish. Okay. I was afraid I'd said the charge is going to diminish. I started thinking about charge. But that's sort of right. Okay, so the current is going to diminish until it disappears, at which point is equal. Now, theoretically, it never disappears because it's approaching exponential. And you can see you're going to have an exponential approach because you've got this negative Q over RC, meaning that the rate at which the charge approaches is going to be proportional to the charge. Okay. It's going to be a decrease. And you're going to end up with this. And the graph is going to look sort of like this. Okay, let's back up a second. I'd have to draw a whole just. This is an exponential approach to the full charge, where the full charge is P. So the charge is EMF times C. Well, that's kind of the big deal. It's interesting now, and we can't do it, but you did some work with systems of differential equations. Well, that's what you get if you got a network of sources and resistors and capacitors. You get a system of linear differential equations. And that's how you analyze it. So if you're going into electrical engineering, you're going to do that. Okay. Or in any kind of engineering that involves electrical. And you know, actually, so this might be the first glimpse of a pretty rigorous application. I mean, you did some applications. You did mixing problems, you did mechanical oscillators, right? Okay, well, pretty soon we're going to do oscillators in RC circuits. We've already got a C now. Okay, and RLC circuits. We haven't talked about inductors yet. That's coming up as far as next week. Okay. There's a total analogy between those circuits and the mechanical. And the well, we'll work out the analogy. Don't know what did the doctor does here? Okay. The capacitor is analogous to the driving force. I don't want to go too much into that analogy. Okay. So among other things, what can I ask you to do? I can't ask you to solve the differential equation, although I can ask you to write it down. And then I can ask you to write down the solution that you need to know. Okay. And maybe the easiest way to do that, just go back and solve basic linear differential equations. Okay. It's easy to solve that as it is to remember this. It's up to you. How well did you learn the differential equations? How easy was that for you? How obvious was it? It's not totally obvious, probably just one, right? But there's a logic to it. Right there's an exponential decrease. And right there is what this whole thing is approaching. This is going to approach 0, and this is going to approach 1. This has got to approach the total charge of the capacitor. And the voltage across the capacitor is equal to the voltage of the source. Okay. Different ways to think about it. You want to understand it in all those ways. Okay. Relevant to what we're going to be observing in lab next week. We're going to observe this exponential decrease, which is going to allow us to determine RC for any circuit. So let's look at the mathematics, what that e to the negative t over RC tells us. The board set up. Okay, let's talk about this expression e to the negative t over RC. Okay. What is e to the negative t over RC equal to 1/2? Can you solve that equation? Give you just a minute. Okay, let's see. We just blurred out again. Pause a second. I'll get this thing to. There it is. Okay. As soon as I threaten to pause, I never go to focus. Where does e to the negative t over RC equal 1/2? Well, we solved it. We did the natural log of e to the negative t over RC. The natural log of 1/2. Well, natural log of e to the negative t over RC, but that natural log is the inverse function to the exponential function. So this is just negative t over RC. And the natural log of 1/2 is approximately negative 0.7. 0.69 something, I think. I always get that confused with square root of 2 over 2, 1 over square root of 2, which is like 0.707. But it's both of them are pretty close to negative 0.7. Okay. So that is 0.7 RC. Okay. Now, RC has units of time, right? Has to have units of time because it's equal to time. Okay. E to the negative t over RC wouldn't be a valid expression if RC didn't have units of time. Team work out the units of time. Okay. R is ohms. Okay. It's voltage over resistance, which is joules per coulomb over whatever resistance is, but then resistance is current times voltage divided by current. Okay, joules per second, coulombs per second, which gives you I know I have to, right now my head is just such that I have to write. Anyway, you just reason it out by the units the way you just and you get seconds. Yeah, it's capacity. Capacity is a joule per coulomb and all that goes together. It's not just per coulomb. Per volt. Put it all together. You get RC is in units of time, and you want to verify that anyhow. RC is called your time constant. In terms of this situation, it's a time required for the current. Ready to do this. I'm just going to say it's time required for whatever you're measuring. The current default of 1/8, which I think is about 0.37. Of its initial value. Or at any point in the fall. It's the time it takes to fall from the 1/E of whatever it is right now. Okay, so you got the current or the value of this thing, whatever you're measuring it is. The picture for the circuit that we started with. Well, okay, let's do that. Got y equals e to the negative t over RC, right? What's the half-life? Well, half-life time is the time it takes from any point, and we could take any 2 points, but we'll start with this point, and the value of the function falls to half. Well, half of this is about this. Right here is delta t, which is 0.7 RC. Half-life. And I'm sure you're familiar with the idea of half-life. No way to get to a competently done differential equations course, and it was very competently done. Okay. I didn't teach it this time. So we know what's competent. You got the idea of half-life. You probably encountered that in some of your engineering. And then the time constant is just plain old RC. It's about that much bigger. It takes a little longer to fall to 0.37 than it does to 0.5. For the capacitor circuit, we have, let's say this is voltage, or let's say it's current. No, this is capacitor voltage. Capacitor voltage versus time. Capacitor voltage here, these are EMF times C. This is what you're going to approach when you close that switch. That's there. I did show the picture again. So you got me there. Okay. That's the acid group. Okay, you start with no charge in the capacitor. You don't have to start with full charge. Capacitor could start being partially charged, could even be negatively charged. Wherever it is, whatever the capacitor is doing, it's going to approach this with the same half-life we got from just the e to the negative t over RC function. Okay. Well, if the half-life is this much, I've been using a fancy C, although you usually won't see it, so let's take them all fancy for right now. Okay, there's your delta to your 0.7 RC. That's approximate. But all I gotta say is 0.697. Okay. Then it's going to approach this thing halfway in this time. And then in that time again, and in that time again, and in that time again, it's going to keep approaching halfway. By the time it's done that 4 times, it's down to 1/16. Right. So we can, okay, here it is. Let's just go halfway. That would be here. So the current's got to go through this way. It's going to be important when we do lab, because you're going to see this in real time on the display. Uh, the other place. Then it's gonna go to half of this, right? So, well, that's gonna take it halfway from here to here. That's gonna put you here. Let's go halfway from here to here. And then halfway from here to here. I said that was about a 16. Now, draw this all that carefully, but you got this one there. And it's still good, it's gonna keep on halfway in the same time here. So you should be able to draw that. Now, something's gonna happen. Just to give you a little foreshadowing. I'm sure it was. It was visible a minute ago. So if anything was missed, all this was visible, some of this got cut off about there. It's all with a store. Okay. What we're gonna do is this. And maybe we're measuring the voltage across the capacitor, or maybe we're measuring the current in the circuit. Okay. It's all going to come out about the same. We've got our asymptote here. We got an asymptote on the other side here. This is EMF times the capacitance, negative EMF times the capacitance. The reverse leads on our circuit, which means that maybe we start here and we let this thing approach this asymptote for a while. Then we switch the leads and we let it approach this asymptote. Well, if our time constant, our half-life is like so. If we get up to here, now this is more than halfway up to the maximum circuit, because we're not going to do it at the time constant. Okay. Then we're going to switch leads, and now it's going to start approaching this. Same EMF, but we're just going to reverse it. Okay. So it's going to approach this with the same time constant. So, you know, we'll do the time constant here. And halfway from here to here is going to be about here. So by the time we get here, it's going to be down to here. And then it's going to continue on a little ways. And then we let it go at the same time we did this, and we switch it back. So now it's going to approach this one again. And let's see, time constant will be about here. It's going to get halfway. Let's see, halfway from here to here, be about here. It's going to come back up to here, and then it's going to continue sawing back and forth. It's always got enough time to get past T-axis, because we let it go for more than a time constant. No matter how low it is here, it can't go any lower than this. It can't be any higher than this. No matter where it is, it's going to get past there. Okay. So what's it going to look like? Work it out graphically and sketch it with some accuracy, and there's a lot of insight to be gained. Then you can write it out as an equation, and we'll toss transform it. You're not gonna have to do that, but you know how to do that. Okay, you got far enough into the plus transfer. You know how to do that, you can solve it. Okay, it's like a step function. You're driving this thing with a step function that looks like this. Because you're doing it this voltage, and then driving it down here, and then you're gonna drive it up there. Okay. You did step function, didn't you? So I just say that for, you don't have to do that, but if you're an electrical engineer and you're gonna get used to it. Okay. Okay, let's see if there's anything else I need to say. These are, those are fundamentals, principles, what happens when you got a capacitor in a circuit and no inductor.